Bismillahir Rahmanir Rahim. My dear students and friends, Assalamu Alaikum. I hope you're feeling well and that you fully digested my previous lecture on equilibrium. Because if you did, then this will make life considerably easy for you, not only in microeconomics, but also in macroeconomics. Equilibrium analysis, a solid understanding of demand and supply will go a long way in your assimilating a good understanding and feel for economics. Now, in the previous lecture, we introduced the topic of elasticity. I'm not going to do a recap of the last lecture because it will take me a full lecture to recap on what we learned in the last lecture. But we introduced the topic of elasticity. And we said that there were different types of elasticity. There was elasticity of demand, elasticity of supply, and I gave you some preliminary tentative definitions. Today, we'll talk about elasticity proper. This lecture and the next lecture will be devoted to a discussion of elasticities. I intend to devote this lecture mainly to the computational and the definitional sides of elasticity. So we'll talk about how elasticity is defined. There are a number of ways in which you could define elasticity. There are also different implications arising from those different definitions. Then there are computational aspects of elasticity. Elasticity can be measured in a number of different ways, and we'll discuss those. Point elasticity, arc elasticity, and other measurement ways. So those are the two foci for this lecture. But before we start discussion on them, I want to put this question to you, to myself as well, that why are we studying elasticities? Why is elasticity important for economic analysis? And the answer is that elasticity is something that many people are interested in. Firms are interested in elasticities. They want to know which consumers have what price elasticity for which products. So that helps them price their products. Because as you know, firms are profit maximizers. They want to get the best price for their product. So by knowing whether the demand for a particular product is elastic or inelastic, they can decide as to whether they can raise prices or lower prices. Then, governments are very interested in the concept of elasticity of demand. Often, the government has to decide to impose taxes. And when confronted with this decision, it needs to have an idea of what the elasticities, the demand elasticities of different goods are. Because as we will show, it pays for the government to impose the tax on goods for which the elasticity of demand is very low. Finally, elasticity helps us explain a number of phenomena around the world. The fact that poor countries suffer from trade problems, trade-related problems, that their imports are constantly rising and their exports are constantly falling. And as we will see, this can also be explained in the context of elasticities. So elasticity is a concept which has very wide and rich applications in the real world. And this is why I've decided to devote this entire lecture to developing a fuller understanding of the definitional and computational aspects of elasticity. Once you've mastered that, then we'll go to the implications, the interpretations, the policy dimension that this concept gives rise to, so that we have a fuller understanding of the concept of elasticity. So let's start today's lecture. If you remember, we introduced a preliminary definition in the previous lecture that elasticity is the percentage change in quantity demanded divided by the percentage change in price. But I want to go a step back and define elasticity of anything as what is shown on the plasma screen. As you can see, it has been defined, elasticity, as a measure of responsiveness which is equal to the percentage change in y, where y is any variable, and I'll define what it is, divided by the percentage change in x. Now in this particular slide, y has been taken as the affected variable, as the variable which is affected by something else. And x here is the cause variable, which causes y to be affected, right? So taking x as the cause variable and y as the affected variable, we can define elasticity as the percentage change in y divided by the percentage change in x. Now let's illustrate this concept a little bit better through the use of a slide. Let's go to our slide. So with y as the effect variable and x as the cause variable, let us define an algebraic relationship between the two. Let's define this as y is equal to fx, where f is a function. Now, let's put some approximation for this function as y is equal to alpha minus beta x, right, where alpha and beta are coefficients. So when you plot this in yx space, this will become a downward sloping line, right, with beta as the slope or a measure of the gradient of this line. Minus beta will be the actual value of this slope, and beta will be the magnitude of the slope. Now, if you recall from calculus, the slope of a function or a line or a curve is basically the rate of change of the variable on the vertical axis with respect to the variable on the horizontal axis. So in this case, the slope of the line, which is equal to beta, is basically a measure of how y changes in response to x. Now, as you can see, this line E is quite steep, right? And I've labeled it as elastic. Now, this simply follows from the definition of elasticity just introduced. That is, elasticity is a measure of the responsiveness of y with respect to x. So a steep curve, in this case, a steep line, basically says that a small change in x causes a large change in y. So a small change in x, in this case, let's say AB, causes a much larger change in y, in this case, CA. Now let's consider another line, and let's label it IE, which basically stands for inelastic. This is much flatter. And now if you take a change QR in x and compare it with a change PQ, a corresponding change PQ in y, you will see that PQ over QR is much less than CA over AB, which was the slope for the previous graph. Now what this tells us is that the steeper the line, the more elastic is y with respect to x. And the flatter the line, in this case, the line IE, which stands for inelastic, the less elastic is y with respect to x. Now let's replace y and x by some real-world figures. You know, as economists, we should always talk about real-world variables. So let's replace y with quantity demanded and x by price. And we get the unfamiliar or infamiliar demand curve. As you know, our typical demand curve is drawn in PQ space. But in this case, we're trying to illustrate how an independent variable P affects a dependent variable QD. So if you draw the same line E in QP space, you can say that a steeper line is consistent with a more elastic demand with respect to price, whereas a flatter line is consistent with inelasticity. However, in order to show what elastic and inelastic means in the context of our traditional or conventional representation of demand, we need to draw this diagram in PQ space. And this can be obtained simply by rotating this diagram, and as we can see, we obtain the diagram shown now. And here we see that the steeper curve now is consistent with inelasticity, whereas the flatter curve is now consistent with elasticity. This change has been brought about mainly because we have swapped the axes. Quantity demanded, which was the dependent variable, is now on the horizontal axis, whereas price, which was taken as the independent variable, is now on the vertical axis. And therefore, the flatter line, in which quantity demanded changes a lot in response to a small change on the vertical axis in price, is now consistent with elastic demand. Now already you should be able to appreciate that we've started talking about the slope of the demand curve. Remember, in the last two lectures we talked a lot about what factors caused shifts in the demand curve. and we did not pay any qualitative attention to what or why the slope of the demand curve was important, or the supply curve for that matter. But here, in the discussion of elasticity, slope is at the heart of the discussion. A higher slope means inelastic demand, a lower slope means elastic demand. Now, coming back to our original equation, y is equal to fx, let us appreciate that both y and x could be anything, any variables, not just q, d, and p. So let's see what the four different configurations are in this case. The first case is obviously what we've discussed, where y is equal to qd and x is equal to price. And this is equal to the price elasticity of demand representation. Then we could have y is equal to qs, where qs is the quantity supplied of any good, and x is still the price. And here we would illustrate the price elasticity of supply. Then we could have y is equal to qd, and x is equal to income. And then in this graph, we would have income elasticity of demand as emerging from the slope of the line. And then finally, we could have y is equal to qda, where this means the quantity demanded of good A, whereas x is equal to the price of B, where it is the price of good B, so where A and B could be substitutes or complements. And this gives us the cross-price elasticity of demand. Now, there could be many other combinations. You could have y is equal to qs and x is equal to costs, y is equal to qd and x is equal to income distribution, and a whole range of possibilities, given that there are a number of determinants of supply and a number of determinants of demand. However, we will stick to just these four because these are the ones which are most used in literature and will be most relevant for our course. Now, let's go to a formal definition of these four elasticities. Let's first of all talk about price elasticity of demand. Now, as you can see, price elasticity of demand is written as P epsilon D, where epsilon stands for elasticity, P stands for price, and D stands for demand. Now, this is just one way of writing elasticity or summarizing the formula for elasticity. But this is a very popular way, and we will be using this notation for our course. Now, note that PED, the order will remain the same. So, the independent variable, which is the cause variable, will come first. So, that is P in this case. Elasticity, the epsilon symbol, will come next. And then D, the affected variable, which is demand, will come last as a subscript to E. So, price elasticity of demand, which shows the responsiveness of quantity demanded to a change in price, is therefore defined as the percentage change in quantity demanded divided by the percentage change in price. So, if, for example, a 20% rise in the price of a particular product causes a 10% fall in the quantity demanded, the price elasticity of demand will be, yes, minus 10% over 20% is equal to minus 0.5. Now, let's look at price elasticity of supply, which will be represented as, yes, P epsilon subscript S. Price elasticity of supply shows the responsiveness of quantity supplied to a change in price. And it would be defined as PES is equal to percentage change in the quantity supplied divided by percentage change in price. Thus, if there is a 15% rise in the price of a particular product, and this causes a 15% rise in the quantity supplied, the price elasticity of supply will be 15% over 15% is equal to 1. Now, as expected, the sign of elasticity in this case is positive, unlike the one that we had for price elasticity of demand. And this is consistent with the laws of demand and supply. Remember that the law of demand was that as the price of a good increased, quantity demanded fell. Therefore, the elasticity or the responsiveness would have a negative sign. Whereas for supply, when the price of a particular product increased, this was consistent with an increase in supply, and therefore any measure of responsiveness or elasticity would have a positive sign. Then we come to income elasticity of demand, which is represented as YED. Income elasticity of demand measures the responsiveness of demand to a change in consumer incomes. It is defined as percentage change in demand over percentage change in income. So for instance, if there is a 2% rise in the incomes of households, and this causes an 8% increase in a particular product's demand, then the income elasticity of demand for that product will be 8% divided by 2% is equal to 4. Finally, we have cross-price elasticity of demand, which is denoted by P subscript B epsilon D subscript A. And what this basically says is that it measures the responsiveness of demand for one good to a change in the price of another good, either a substitute or a complement. So it would be defined as the percentage change in demand for good A divided by the percentage change in the price of good B. Note that the independent variable in this case, which is PB, comes at the beginning of the notation, whereas the dependent variable, which is the demand for good A, comes after as a subscript of epsilon, which is the symbol for elasticity. The concept of cross-price elasticity is useful to a firm which wants to know how responsive the demand for its product will be to a change in the price of its rival firm's products. So if, for example, the demand for butter rose by 2% when the price of margarine, which is a substitute, rose by 8%, then the cross-price elasticity of demand for butter with respect to margarine would be 2% divided by 8% is equal to 0.25. If, on the other hand, the price of bread, which is a complement, rose, the demand for butter would fall. So if a 4% rise in the price of bread led to a 3% fall in the demand for butter, the cross-price elasticity of demand for butter with respect to bread would be, yes, minus 3% divided by 4% is equal to minus 0.75. So we've looked at the 4 different types of elasticity, but discussed the intuition of just one of them. We will, inshallah, discuss the intuition of all 4 in our next lecture. So, my friends, we've discussed all the 4 types, the major types of elasticity. We've defined them. We've discussed the intuition of just one of them, which is cross-price elasticity. But rest assured, we will discuss the intuition of all 4 in our next lecture. So let's now pause for a moment and discuss why we have used proportions and percentage changes in quantity supplied versus percentage changes in price rather than absolute changes in quantity and price. Now, there are 3 reasons for that. One is that by using percentages or proportions, we avoid the problem of comparing two variables which are qualitatively different. So quantity is measured in units and price is measured, let's say, in rupees. And therefore, by using percentages, we avoid relating units to rupees, right? The second problem that it helps us avoid is that of what size of units to choose. So, for example, a jump from rupees 2 to rupees 4 could be described as an increase of 200 paisa, or it could be described as an increase of 2 rupees. But by using percentage increases, we avoid that problem because both will give us the same answer. Because in both cases, the price is being doubled. So there is a 100% increase. The third problem that it helps us avoid is that we can then know how to define big or small changes. By looking at, say, rupees 2 and rupees 4, we can't say whether that's a big change or a small change. But when we translate it in the form of percentage changes, so that's 100%, so that's a big change, or that's 50%, that's slightly smaller, we get an idea, a sensible idea of how big or how small the changes are. So that's one important reason. There are three important reasons actually why we use percentage or proportionate figures and not absolute values in measuring elasticity. Now let's discuss two other small things that we found or discovered when we calculated different elasticities. One was that we often obtained different signs. Sometimes we obtained plus 0.5, sometimes we obtained minus 0.75. What do these mean? And as I pointed out earlier, the signs here merely show us the direction of responsiveness. So if the direction of responsiveness is the same, then the sign will be positive. If the direction of responsiveness is the opposite, then we'll have a negative sign. So when you relate quantity demanded to price, you'll have negative value for elasticity. But when you have, let's say, quantity supplied and then you relate it to price, then you'd have a positive sign for elasticity. Now thirdly, what about the value that we are finding? One is sign, one is value, the magnitude of elasticity that we've computed. And really, the notion of elastic or inelastic depends on the magnitude, the modulus of that value that we've obtained, not on the sign. So whether you have minus 3 or plus 3, that will not tell you whether that will be that the concept at hand is elastic or inelastic. What that will tell you merely is the sign. But it's the 3 there, the 3 which captures whether this is an elastic concept that we are talking about or an inelastic one. Now, with this, keeping this focus on the magnitude of elasticity that we've computed, we can set up the whole spectrum of values that elasticity can take. And these spectrum of values is from 0 to infinity. Now let's see how this helps us formulate the first rule of elasticity. In all, there are 3 rules. So let's look at our first rule, which we'll illustrate through a slide. Now, since we are talking only about the absolute values and not the signed values of elasticity, then the range that elasticity can take is from 0 to infinity. So bang in the middle, we have the elasticity value of 1, which is called unit elasticity. Now, in the context of elasticity of demand, if we draw this in PQ space, we'll get a curve whose gradient is neither too large nor too small, somewhere in the middle, right? So that's the unit elasticity case. Then if we move right, that is, for elasticities greater than 1, we move into curves whose gradient is very small. So a small change in price causes a large change in quantity demanded. As we move further to the right and go towards infinity, the demand curve becomes perfectly horizontal. So an infinitesimally small change in price causes a very, very large change or an infinite change in the quantity demanded. So this is called the perfectly elastic case for demand. Then if we move left from the unit elasticity case, that is for elasticity less than 1 and between 0 and 1, we have the inelastic case. In this case, the demand curve is quite steep, so that a small change in price or even a very large change in price will cause only a small change in quantity demanded. To the extreme left is the case of perfect inelasticity or zero elasticity. And in this case, we basically have a vertical line. The demand curve is a vertical line in PQ space, so that an infinite change in price also does not cause even a tiny change in the quantity demanded. So this basically is the whole menu of values that elasticity can take, and we can depict them through these different graphs. Now, given that understanding of what is elastic and what is inelastic in numerical terms, let's now stab into a discussion of the relationship between revenue and elasticity. Now, if you remember, in the beginning of the lecture I mentioned that elasticity is very important for firms. Firms are profit maximizers, and at any time they want to find a way to maximize the price that they can charge for their goods, because this will in turn maximize their profits. Elasticity gives them that hint. price elasticity of demand in particular. So if a good has very high price elasticity of demand, firms will hesitate to increase their price because they will know that the quantity demanded will fall very much. However, if the price elasticity of demand is very low, that is, you are in the realm of inelastic demand, then firms will readily increase price because they know that the quantity demanded will not fall sufficiently. Now, at the heart of this, you might feel that there is some connection between revenue and elasticity, because both notions involve a relationship between quantity and price. Elasticity is percentage change in quantity divided by percentage change in price, whereas total revenues are merely price into quantity. So when you're talking about unit elasticity or inelastic demand or elastic demand, you are basically making a statement on what is going to happen to total revenues when prices change. Let's try to explore this particular relationship a little bit further through the use of a slide. We take the case here of two profit-maximizing firms, each facing very different demand curves. These different demand curves are shown in the figure below. Note that here we are now dropping the assumption that firms are price takers. That is, we are dropping the assumption that there is perfect competition. We are assuming that firms can choose their own price and therefore face a downward sloping demand curve. We will examine the circumstances under which firms can control prices later on in later lectures as well. Now, as you can see, firm 1 can consider raising its price quite substantially. Let's say it is considering to raise its price from rupees 6 to rupees 10. Will its level of sales fall considerably? No. As you can see, its level of sales will only fall by 10. That is, from 100 units to 90 units. More importantly, the total revenue that the firm gets, that is price times quantity, will actually rise from rupees 600 to rupees 900. Note that revenue or total revenue at any point of the demand curve is simply the rectangle that can be drawn from the origin and linking the points of equilibrium quantity, equilibrium price, and the point on the demand curve. So for firm 1, when the price was 6, the total revenue that the firm was making was OBTC. That's the area of the rectangle OBTC. Now that the firm has increased its price to 10 rupees, the new rectangle, that is the new total revenue that the firm will make, will be OAFD. And as you can see, the new rectangle is bigger than the first one. The area of OBTC was 100 times 6, that is 600 units, 600 rupees in a way. Whereas the area OAFD is 90 times 10, which is rupees 900, which is what I said earlier as well. So by increasing its price, and quite substantially, from rupees 6 to rupees 10, the firm has actually increased its total revenues. So this is the principle. If total revenues rise by raising your price, then the firm faces an inelastic demand curve. Now let's look at the case 2, the firm 2 and the demand curve that it faces. As you can see, firm 2 will hesitate to raise its price, because even a relatively small increase in its price from rupees 6 to rupees 7 will lead to a very substantial fall in its sales from 100 units to 40 units. In terms of total revenue, you can see that revenue will fall from rupees 600 to rupees 280, which is a very substantial fall. Graphically, you can see that before the increase in price from rupees 6 to rupees 7, the firm was making total revenues of OVZS. That was the rectangle which gave the total revenue that the firm was making before. And this was equal to 100 times 6, which is equal to rupees 600, which is the same as what the firm 1 was making. Now, when the increase in price has taken place and the equilibrium point has moved to point U, the new rectangle giving the total revenue is OYUR. And the total revenue now is 40 times 7, which is equal to 280 rupees, which is what I said earlier. So here, total revenue has fallen by raising the price. And this is the case of elastic demand. Now let's see whether this scenario fits in with the understanding of elasticity, the numerical elasticity calculation that we saw or went through earlier. Now in case 1, the case of firm 1, we can calculate the elasticity as, the change in quantity, the percentage change in quantity demanded by the percentage change in price. So what is the percentage change in quantity demanded? It is simply 90 minus 100 whole divided by 100, which is minus 10%. Whereas the percentage change in price would be 10 minus 6 divided by 6. And by dividing these two different terms, we get minus 0.15, which is consistent with an inelastic demand. As we can refer to our original menu of values, we can see that minus 0.15 fits into the category of inelastic demand because its absolute value is between 0 and 1. By contrast, let's look at what's happening to firm 2's elasticity. Now in moving from Z to U, the firm's elasticity will be calculated as follows. Percentage change in quantity would be 40, which is the quantity after the increase in price, minus 100, which is the quantity before the increase in price, and whole divided by 100. This will give the percentage change in quantity. And now you divide this by the percentage change in price, which in this case would simply be 7 minus 6 whole over 6. Now dividing these two terms, we will get a price elasticity of demand of minus 3.6. Now as you can see, the value of this elasticity is greater than 1 and less than infinity. And therefore this will categorize as elastic demand, not inelastic demand as we got in the case of firm 1. So if you look carefully, whether total revenues rise by raising your price or fall by raising your price is closely associated with whether demand for a particular product is elastic or inelastic. So if total revenues rise by raising the price, demand is inelastic, but if total revenues fall by raising the price, then demand is elastic. Now we've discussed how elasticity can vary across two different demand curves faced by two different firms. But elasticity can also vary along the same curve. And let's illustrate this through another example. Here we have a single firm with a downward sloping demand curve. Price is on the vertical axis, quantity demanded is on the horizontal axis. Let's now see the impact of reducing the price on total revenues. That is, let's say, the impact of moving from K to L on total revenues. As you can see, the total revenue increases from 64, which is 8 times 8, to 96, which is 6 times 16. And therefore, total revenues have increased. Now, if you look at what the elasticity of demand is in moving from K to L, you can find that simply by calculating the percentage change in quantity demanded divided by the percentage change in price. Now, what's the percentage change in QD? That's simply 16 minus 8 whole divided by 8. Whereas the percentage change in price is 6 minus 8 divided by 8. Note that in calculating this, we've taken the initial position as K and that we are moving to L. So the change in price and in quantity are being taken with respect to the price and quantity prevailing at K. Now the elasticity of demand in moving from K to L is equal to minus 4. Now let's look at another segment of the same demand curve that the firm faces. Right? And now we are taking points G and H on the same demand curve. And let's see whether we get the same answer for elasticity or not. Now let's study a movement from G to H. In this case, we see that total revenue actually falls from 84 to 36 instead of rising. Why is this happening? Let's see what's happening to elasticity in order to understand this better. The elasticity of demand in moving from G to H will be calculated as 36 minus 28 whole over 28 divided by 1 minus 3 whole over 3. And this gives an elasticity of minus 3 by 7, which as you can see is less than 1 in absolute terms and therefore categorizes as inelastic demand. So that's extremely interesting. We've just seen that elasticity does not only take different values for different curves which have different slopes, but elasticity can change its value along the same curve. So when we were at the higher point of the curve, elasticity was higher. The elasticity of demand was minus 4. But when we went along the curve in a southeastwardly direction, then we found that the elasticity value went down and we went into inelastic demand. Now, why does this happen? In order to understand this better, let's develop the concept of arc elasticity of demand. Now, the concept of arc elasticity of demand basically says that we should be able to develop a notion of what price elasticity is across a segment of the demand curve and not just on a particular point. Here we said that elasticity varies across two different segments of the demand curve. But when we talk about arc elasticity, we are saying that elasticity can vary across 2 points of that segment as well. Let's try to understand the concept of arc elasticity a little bit better. Let's go to our slide. Now let's study the segment KL a little bit better in our previous example. We see that if we study the elasticity of demand in moving from K to L, that is, K is the starting point and L is the finishing point, so that we are studying how quantity demanded would change in response to a change in price, we will calculate elasticity as follows. Elasticity will be calculated as 16 minus 8 divided by 8 whole divided by 6 minus 8 divided by 8. And this gives us the same earlier answer of minus 4. But now consider what happens if we take the starting point as L and the finishing point as K. So we are moving upwards from L to K. That is, we are studying what would happen to quantity demanded in response to an increase in price from 6 to 8. Now if we calculate elasticity and apply our formula, we'll get 8 minus 16 whole divided by 16 whole divided by 8 minus 6 whole divided by 6. And this gives us an elasticity of minus 3.2. No doubt, minus 3.2 also falls in the same range as minus 4 does, so that they are both elastic. However, there is a substantial difference. Minus 3.2 or minus 1.5 is substantially less than minus 4. What happened? Well, what happened is basically that the starting point made all the difference. In moving from K to L, the starting point was K, and the units of price and quantity used as the points of reference from which change was measured were those obtaining at K. Whereas in moving from L to K, the starting point was L, and we used 16 and 6 as the starting quantity and price respectively. Now, in order to avoid such problems, that is, avoid problems of obtaining different values for elasticity in moving from K to L and L to K, we can develop the concept of arc elasticity of demand. And that basically consists in the following. We take change in quantity divided by quantity and divided by change in price divided by price. Now, the quantity appearing in the denominator in the first expression can be taken as the average of the quantities obtaining at K and L. Similarly, the price which is appearing in the denominator of the right expression, we can again take an average of the price obtaining at K and L. So the elasticity, the arc elasticity for the segment KL can be computed as follows. 16 minus 8 divided by the average quantity at K between K and L, which would be 12, which is the average of 8 and 16, whole divided by 6 minus 8 divided by the average price obtaining between K and L, which is 7. And this gives us an arc elasticity of minus 7/3, which is just over minus 2. Similarly, if we calculate elasticity Lk, that is in moving from L to K, we can get the same answer again, only that we'll have 8 minus 16 over 12 in the numerator and 8 minus 6 over 7 in the denominator. And again we'll get minus 7/3. So the average elasticity along the arc KL or LK is minus 7/3. So as you can see, the arc elasticity concept is very useful when we are talking about demand curves or segments of the demand curves across which elasticity is not constant. At least now we can talk about a measure of average elasticity prevailing over K to L and avoid the problem of starting points, that is either starting from K or starting from L. Now that we have developed a concept of elasticity, the average elasticity prevailing over a segment of the demand curve, and we gave the example of KL or LK, we can now revert back to the concept of point elasticity. Now, point elasticity is an important concept, especially when we are dealing with demand curves that are not straight lines, like the example that we just took. Demand curves can be curves, downward sloping and with some curvature. And this would usually happen when the demand function or the demand equation involves a term, a quadratic term in price. So you could have QD is equal to A minus BP minus CP squared. And we'll look at an example of that. So point elasticity is an important concept when it comes to demand curves which have some curvature. Let's look at a slide and our final set of slides to illustrate this. Now we recall our earlier formula for elasticity, which was simply as change in quantity over quantity divided by change in price over price. This can be rewritten like delta Q over delta P multiplied by P over Q. Now, since we want to measure price elasticity at a point on the demand curve rather than between 2 points, it is necessary to know how quantity demanded would react to an infinitesimally small change in price. Now, an infinitely small change can be signified by the letter D, and you will have to recall your understanding of basic calculus for this. So the formula for price elasticity of demand can thus be rewritten as dQ over dP multiplied by P over Q, where the D has simply replaced the delta. Now dQ over dP is the differential calculus term for the rate of change of quantity with respect to a change in price. And conversely, dP over dQ is the rate of change of price with respect to a change in quantity demanded. At any given point on the demand curve, dP over dQ is given by the slope of the curve, its rate of change or tangent. Now, for a straight line, as you know, this slope is constant. But this does not mean that the point elasticity is same across the line as well, at all points of the line as well. A straight line demand curve will have a different elasticity at each point on it. The only exceptions are a vertical demand curve, where price elasticity of demand is equal to 0, and a horizontal demand curve, where price elasticity of demand is equal to infinity. Let's look at our previous example, which gave a straight line demand curve. Now, as you can see, at both points K and L, dp over dq, that is the slope of the line, is equal to minus 1 over 4. Thus, dq over dp, which is just the reciprocal of dp over dq, would be equal to minus 4. But P over Q, which is the other part of the elasticity formula, is different at K and L. At K, P over Q is equal to 8 over 8, which is equal to 1. Therefore, point elasticity is equal to minus 4 times 1 equals minus 4, which is what we obtained earlier. But at L, P over Q is equal to 6 over 16, which is equal to 3 over 8. Therefore, point elasticity is equal to minus 4 times 3 over 8 is equal to minus 3 over 2, which is also what we obtained earlier. Now let's illustrate the concept of point elasticity in the context of a quadratic demand function. Let's take the example QD is equal to 60 minus 15P plus P squared, where QD is measured in thousands of units. From this, the following schedule and graph can be constructed. And this is included in your lecture handouts. I would like you to go home and practice how this has been obtained, both the setting up of the schedule and the drawing of the demand curve. Now, once we've drawn the demand curve, we can easily calculate point elasticity by using calculus. To do this, you will need to know the rules of differentiation, and I imagine that you already know those. Remember the formula for point elasticity. PED is equal to dq over dp multiplied by p over q. The term dq over dp can be calculated by differentiating the demand equation with respect to p. So you get qd is equal to 60 minus 15p plus p squared, and dq over dp is equal to minus 15 plus 2p. Thus, at a price of 3, for example, dq over dp is equal to minus 15 plus 2 times 3, which is equal to minus 9. Thus, price elasticity of demand at a price of 3 is equal to minus 9 times p over q, which is equal to minus 9 times 3 over 24, which is equal to minus 9 over 8. Now you tell me whether at point 3 we have elastic demand or inelastic demand. My answer would be it is elastic, because 9 over 8 or minus 9 over 8 is in absolute terms greater than 1, and therefore falls in the elastic region as per the first rule of elasticity. Now with that, my friends, we come to the end of today's lecture. Now note that you've been armed with some very powerful concepts. You know how to define elasticities. You know how to calculate elasticities. You know what the relationship between total revenue and elasticities is. You know how elasticity can change along a curve, along a straight line. You know how elasticity can change along different points or different points of small segments. And that is why we developed concepts of arc or average elasticity and the concepts of point elasticity, both in the context of straight line demand curves and in the context of demand curves with curvature. Now, in our next lecture, we will talk about a little bit of intuition. We'll talk about the determinants of price elasticity of demand. We will also talk about the other types of elasticity that we defined today: income elasticity of demand, price elasticity of supply, and then cross elasticity of demand, cross price elasticity. These are very important concepts, and we'll try to get to the heart of these. And if we find time, and I'm sure we will also talk about how government policy or firms' policy can react to these different notions of elasticity, to these different values that elasticities take. And believe me, it has very important implications not only for microeconomics, but also for the study of macroeconomic problems that we will take up in the second part of this course. So, my friends, that brings us to the end. I hope you enjoyed today's lecture. I certainly did. I always enjoy teaching elasticities. Now, don't get bogged down by the mathematics that we covered today or the graphical illustrations. They're actually intended to make life simple for you. And if you have really developed a good and solid understanding of the mathematics and the graphical intuition, believe you me, life will become very simple for you in the future. Now, after the next lecture, we'll be delving into utility theory and the underlying intuition of supply analysis. And in that, elasticity and the way total revenues are calculated from these graphs and how equilibrium is reached, and those things will become very important. So what I want you to do is to go home, try some of those questions that I've put up for you on the web. They involve some notation, they involve some calculations. Practice with that, and if you do practice and come home with a good, solid understanding, then tomorrow's lecture or the next lecture will be very productive for you, because we'll be talking about the intuition of elasticity in that. So it's Khuda Hafiz and Assalamu Alaikum. The next lecture, we'll be delving into utility theory and the underlying intuition of supply analysis. And in that, elasticity and the way total revenues are calculated from these graphs and how equilibrium is reached, and those things will become very important. So what I want you to do is to go home,